Today we're going to move on with our transportation planning section. This is chapter 8 in your book. Talking again about trip generation and then looking at our transportation analysis zones, which we worked on at the end of the last lecture through that. The last time we did what was a linear regression based model for predicting how many trips people were going to take. And the book also has a section on a different method, which is using the Poisson distribution. And if you remember, we used this before when we were looking at traffic signals, and we were trying to predict if we know what an average rate of something is, if we know what the average value is, we can use Poisson to calculate what the probability of that of a number of things happening based off of that average. And so if we had an average of 12 cars a minute arriving at a signal, we could predict what's the probability of 0 cars arriving in a minute. What's the probability of 1 car arriving during that minute? What's the probability of 2 cars arriving for that minute? So if you remember back to that section we were doing in signals, that's where we used Poisson before. And it works well if you know what the average rate is, right? And so, the thing they like about this with trip generation is that if you want to figure out what's the probability of a discrete number, 0, 1, 2, 3, an integer value, if you want to know what the probability of that is, right, that's where this Poisson jumps in. So what's the, and again, it comes out of what's starting with what's the expected number of vehicle-based trips, for a certain activity. We can then predict what the probability of 1 trip or 2 trips or 3 trips is from a certain household from there, or from a group of households that have similar characteristics. Right, we can scale that up to cover all of that. So it's a little bit different way of looking at it. Before we calculated what the expected number of trips was, and we just left it there. But what if, what's the probability of these other things happening? That's where we would use this. And this is a little bit newer modeled. So linear regression is how we normally do it. That's been more the classic way of calculating our trip generations. This is a little more newer method being used through that. So this is our standard Poisson setup. The Poisson equation should look fairly familiar, right? Lambda is usually the average value of something, whatever it is. T is our interval, and that's the number we're looking at in that interval, right, through there. So the probability of one vehicle arriving, one trip being generated during a certain time, we'd plug in 1 here, we'd plug in 1 there. Lambda is the average, and E is the natural exponential function, right, through that. So we can plug all that in, and we can figure that out, right? And how would we use that? Well, we'd use that. And first we have to define how do you calculate lambda? Lambda, it's kind of weird. Lambda's got E in it as well. And so we take E to the BZ, and these are vectors of coefficients and for household characteristics. And you're going to show you an example here in a second. This is going to look pretty familiar to you from what we just did before. So this vector of household characteristics, this is these defining values that we've used before. So how many people live in the household, how many cars they own, what's their income, and other there may be other things that are significant that we throw into that, right? And so that's you're going to see here we define that and then use it. Lambda will come that's our expected value or our average value. This is the number we would expect from a household given certain characteristics, B and Z, which we're going to define here in a second through there. And it depends on what data you have available, how you define that, but you'd have to go through an analysis, again, using survey data to figure out what these vectors are, right? So you survey a bunch of households, and then you find out that, well, households with 3 people in it and 2 cars take this number of shopping trips and this number of work trips and this number of social recreational trips and so forth. And that's how you define these vectors. And that's how you would differentiate those and finally use them, right? And you come up with a table, basically, in the end, saying that here's, based on all this data we've collected, this is our reasonable approximation of how many trips for whatever reason, a household with these characteristics is going to make, right? And that becomes our expected value lambda, which we're going to then come back over here and plug into this Poisson equation. Then we can calculate the probability of number of trips based on that expected value. All right, so before all we had was an expected value. Well, now we can also fine tune and we can look at, well, if there's, what's the probability of no trips? What's the probability of 10 trips, from this household? Right? There could be some, there's some distribution, right, through that. What does that distribution look like? That's what we're going to use that. So here's an example, right? We're going to go back to the shopping trips, number of shopping trips a household makes. And so it's defined as, we have, crunched the data and we have analyzed it and we have calculated that it's, this is the function that describes how many trips a household will make for shopping trips, right? So it's negative 0.3 times 0.03 times the household size, so number of people in that household, plus 0.02 times the household income in thousands of dollars, right? So income is often related to like a shopping trip, right, through that. And then 0.05 times the number of vehicles owned in the household. Now, if you remember from the last lecture, I used the same example, but it has a lot different coefficients. The coefficients for all these things are very different through there. That's because this is a different kind of a model, right? This is an exponential model using the Poisson distribution. So when we crunch the data and do the analysis, we'll come up with different coefficients because we're using e to that factor versus before it was just like a polynomial least squares distribution where we had a b term, kind of a y-intercept, plus some factor times the next variable plus another factor times the next variable and so on, right? We did it that way. So these are different coefficients because this is set up as a different kind of model, and so when you reduce this to find those coefficients, it's a different process, right? It's not a least squares, it's a Poisson distribution. So we're using a different process to find those. So that's why those numbers are different in this example through there. So we've got a household of 3 people, an income level of 50,000 and 2 vehicles in the household. Right? So what's the number of expected shopping trips you'd use, right? So based on this formulation, right, our BZ is just going to equal that, which does look, as far as the setup, it looks fairly similar to before. All right, but the instead of before our t just came out, if you plugged in all those expanded polynomials, you would end up with, I guess it's not really a polynomial, it's different factors times a coefficient. You just ended up with the expected number of trips. Well, now we plug this number in, this vector, they call it, in this case, into e to that power, and this is our expected number of trips. So if we plug that in, this 0.89, e to the 0.89, our expected number of trips from this household is 2.44. Right, so you can see why we couldn't have used those original coefficients we had from the last time in that example, or we'd have a huge number of trips, right? We'd have like 10 or 12 trips. That's probably not likely, right? So this is reformulated to be used in a exponential function like this, e to the whatever power. And we ended up with, our expected number of trips is 2.44, right? Or in previously, the way we talked about the Poisson function, we'd say, well, this is the average expected value, right? So this would be the average, right? We expect the average household to take 2.44 trips per day. We can also call it the expected value is 2.44 trips per day for shopping, right? From a household this size, right? So that's our most likely number of trips. Most likely one is going to be 2.44. That's the expected value, right? But we can, just like before now, we can plug this into the Poisson distribution and as formulated as such, right? And now we can say, well, what's the probability that this household makes no trips? So we plug in 0 for t. Trips is 0. Our lambda is that 2.44. Don't forget there's a negative here. That'll catch you, right? And I'll plug in 0 for the t's, and we end up with, well, the probability that a household that is expected to make 2.44 trips, their probability of making 0 trips is about 9%, more or less, right, through that. And now we can do a distribution, right? We can plug that in, so that's probably 0 trips. We can do this distribution like we did before with the number of vehicles arriving. What's the probability of 10 vehicles arriving while the signal is red, right? Remember that was the example when we did in traffic signal systems. with the Poisson distribution. So here's our probability, right? 0, that's at 9%, right? It's the probability goes up until we pass essentially probably 2.44 would be the highest probability if that was it. But we're using discrete numbers. We're using integers. And then the probability drops as we go through here, right? Here's the graph of that, right? And we know the expected value is 2.44, so we're not surprised that 2 has the number of the probability of this family taking 2 shopping trips is the highest probability, right? And one reason researchers like this Poisson distribution is because a family can't take 2.44 trips. They're either taking 2 or they're taking 3, and so we can see that the highest probability is that they're going to take 2 out of that. But you can get this distribution now, and you can kind of get a better picture sometimes of how many trips are being generated for a particular use based off this probability. Right through there, our expected value is 2.44, but maybe it's a very high peak, or maybe it's a very low kind of lower, flattening the curve, as we say now, kind of a lower function, through there. So that's where this Poisson distribution, can be used. It's just an alternative method of figuring out what's the expected number of trips, what our trip generation is, and it gives you what before we didn't have in the other formulation is we wouldn't have known then what's the probability of 3 trips is. All we knew is the expected value. And now using this Poisson, we can figure out, well, what's the probability that they're going to take 4 trips? And how would we use that, right? So what if we want to have a 95% accurate model, right, through there? So if you added up these percentages, you can get a cumulative percentage. And then you say, well, even though our average value or our expected value is 2.44 trips, right, but some people may take more trips, and they may be, maybe 4 would be our 90th percentile. I haven't added all these up, but it may be that, right, through there. So what's our if you want to be a higher confidence level, I guess, through this, not just the average value, but said, well, from a certain, if we added up all the households in this neighborhood, in this one zone, right, we might expect 100 trips coming out of there based off the average value, but the 90th percentile value is like 140 trips might be coming out of there. Okay, so that's gives you a little bit of a sensitivity analysis for your trip generation. Right, and you can get that through this model, setting it up this way through there. So that's another use for that. But again, it's just an alternative way to calculate trip generation. So those are the two that we talk about in the book. I'm sure there's others that are in the research out there, but these are the 2 more common ones we use. Least squares is the most common. The Poisson is a newer one and is not used as much, but it's an option. Right out there, and it gives you a little bit different information. Right, you can see how it's formulated through there. It gives you that little different information. Well, so now jumping back to where we left off last time, back to these transportation analysis zones, right? And we were talking about how we break by geography. We break a region into similar zones, similar sizes, similar uses within it, right? So we like to break that. This is hopefully 37 is mostly all residential, right? Whereas these smaller ones are probably the downtown area. Maybe they're all more commercial, right? And it helps to break things into kind of more of these homogeneous zones, because then we can analyze them better. Because we know, well, these are all single family homes. That's going to have similar characteristics probably through there, and it'll be a little more accurate versus mixing things into kind of mixed use zones. And there always is a little bit of mixing, but we try to keep it as cohesive as we can, right, through there. And before we're talking about this trip generation, right, to plug these trip generation values in now, we want to apply this to an entire zone, to an analysis zone, and keeping these things homogeneous is going to be helpful for doing that. Right, so we can model the number of trips coming out of here better. And if we know that one of these zones here has a lot of office space and a lot of employment for office, right, it's easier to model how many trips are going to go to there because it's more homogeneous, right? It's the larger attractor in that sense, right, through that. And you can have both attractors and production in a similar zone, and we'll talk about that in future lectures. Through there, you can have inter-trip or inter-zone trips, and that's a thing, right, through there. But in the end, we're getting down to how many people are driving on this road, how many people are driving on that road, how many people are driving on that road, right? We're down to that network model and where we want to get to. And to do that better, we have to have fairly accurate zone descriptions and good resolution where we need it, right? And so if we're worried about how many people are coming into downtown, we're going to need some smaller zones down in here so we can model it better. And I showed you the example from Chicago last time. Right down near the loop, they have very small zones, a few blocks per side through that. Whereas out further away from Chicago, they have very large zones that cover sometimes half a county almost through that. They don't need the resolution out there. They need it near downtown because they're trying to model how many people are coming into downtown through that. So we're back into these analysis zones, and we talked about these are some of the factors, right, that we're going to use as inputs through there. And we had a much bigger list before, but here's some of them, right? And so just in each one of these zones, you have to figure out all of those factors within each of those zones. So what's our population inside that zone? What's the average population per household in the zone? What's the average income? How many vehicles do these households own within that zone? The family size, that's the household population through there. What's the age, right? Sex, employment status, all those things can affect how many trips people make. And there's more, right? We had a lot more, right? So that's a lot of data, right? Where do you get all of that data, right? Isn't that hard to come up with? Yeah, that is a lot. Where do we get it? Well, get it from the government, right? So right now, the census is out. You or your parents may have gotten a card saying you've got to fill out the census. I think April 1st was Census Day. For that, you're supposed to fill out the census. That's where we get a lot of this, right? So the U.S. Census Bureau gathers this data, and they drop it into census blocks. They drop it into geographical regions for us, which, not surprisingly, we often use as our transportation analysis zones because we have the data for it. Right. And so that's where we find out the household data. Right. So the way the census works is they send out a general census to everybody. It's supposed to every physical address they know of. They send out the census. They send out census workers then to make sure they didn't miss anybody within the area, right, through there. Some people get an expanded census form, and that asks even more questions, like how many rooms are in your house, do you own your house, how many cars do you own, do the people in your house own, and so forth. And it's a sample size, so not everybody gets it, but it's a big enough sample size we can make assumptions then about everybody in that region, right? What's the average car ownership rate, right, for that, and so forth. And that's where we get a lot of this. And then also the Census Bureau also puts out an American Community Survey, and that's more frequent. And I'm not sure how many years in between it is, but it is more common. It's more often than 10, which is what the normal census is, right? So every 10 years we get a good snapshot of the entire population and where people are living and in what zones. And then we do this American Community Survey more frequently. And it's not everybody gets that, right? So they're going to take a sample size. They're going to send out this survey, and it has a lot more questions related to transportation and movement, right? And where do you work, and how many days a week do you go there, and how many cars do you own? Do you take transit, and so forth? We get a lot better data for our modeling piece out of this American Community Survey. And again, it's updated intermittently. The real good population data we get once every 10 years. And then, like I say, there's some intermediate checks on that the Census Bureau does in between and runs through that. And what they end up with is the census blocks, right? And this is what the census blocks look like around Valparaiso. And these are fairly big, but not too bad, right? You could almost break it down and use this as our transportation analysis zones if you wanted to. And you can break the census data into smaller pieces, but this is their standard blocks that you get out of that. And that's where we really get most of our data. And if you're happy with these blocks, then don't touch them, right? Because they're already done for you, right? All that data is listed by these blocks. And so we can plug that right into our modeling then when we do our transportation demand modeling. Right. And what's some of the limitations is that, right, we don't know exactly the population particularly at any given year. We know it pretty accurately every 10 years because we have to count everybody in the country every 10 years by law. Through there, everything else is an estimate, and they update those estimates, sure, but they're a little bit off probably. Through there, other things that we don't know is employment, right? And that's often something we want to know. We need to know. We would like to know how many people are employed in a certain area because that is an attraction. We're going to talk about that more in future lectures. But we know where people live. We know that a lot better. We have much better data about where people live than where they work. And so we're trying to predict where people are going during the day. Well, you tend to go to work, right? So, well, maybe not anymore. But if you're not working from home, you're going to get out on the road. You're going to go somewhere, and that's what we're trying to model. That's the whole point of travel demand modeling. And employment is a big piece of that. Just think about our peak hours, our AM hour, peak hour, and a PM peak hour, and that's probably people going to work or coming home from work, right? So that's important to know. It's much harder to figure out where people live, what zone they live in. It's a lot easier to figure out where they live. So that's one of our limitations on that. The other things we need to know is where are the roads, what's the capacity of the roads, what do they link to, right? So if we go back to our TAS, that's not the TAS. If we go back to this TAS description and showing our analysis zones, right? One of the big pieces in here is where are the roads and what are they linking to, and through that. So if we have a high population living here in zone 52, and we've got a lot of commercial activity over here in 27, right? We want to know that. We want to know what roads connect 52 over here to 27. What's the capacity of those roads? How fast is it to go through there? On that, how many lanes did they have, and so forth. And we're going to see where we need that further, right? So we started with, we're creating these zones and calculating the data for it. The other big piece of data we need, or what is the transportation network and what's its capacity and where is it physically, right, through there. So that's this next piece, is what is the network. So how do we link these nodes? The nodes is the centroids of those transportation analysis zones through there. Which zones have a lot of residential, which zones have a lot of commercial, and it makes sense, right, that people are going to want to go from the residential areas into the commercial, into the working areas, right, and back through there. So that's this network. That's how that's important to that is how do they relate to those high population centers and those high work centers, right, through that. And what level of detail we need, again, even with these roads, is depending on what we're trying to figure out. Right? If we want a really detailed model of the city of Valparaiso, we're going to put in probably most of the roads. We're going to leave out some of the smallest ones, but we're going to put a lot more roads in versus if we were trying to model the regional, all of Northwest Indiana, we're going to leave out most of the small roads in Valparaiso and only have the major ones going through it because we don't care about the smaller ones and on that scale. So knowing how you're going to use these models, it's important about when you're building it, knowing how it's going to be used is important so you know which roads you need to add in, which roads are going to be important. And it all depends on how much accuracy you want at a small scale. Through there. Other things we need to know link speed. So that's like our free flow. So this sounds a lot like that level service calculations we did before, right? We need to start off with what's our free flow speed. And then these computer models, they load those networks. They start adding cars to it. And then, based on characteristics of that road, how many lanes it has and how, what its capacity is and so forth. Once the computers start adding the cars, there's like a feedback curve almost, right? As you add more vehicles, that speed drops, right? And then you add some more vehicles and the speed drops even more. Well, then people were probably going to want to use a different road if the speeds get too low on a certain link, right? And so it's this dynamic assignment through that. And that is one of the steps in travel demand modeling is trip assignment. So where are we putting the vehicles? So if we're looking at the highway network, which roads are people driving on, right, through that. And so we go through there. And the same thing works if you're looking at transit, so mass transit systems. It's very similar in that we would look at where's the bus routes, right? And what's the capacity of the bus routes and so forth. And what's the travel time, which would include waiting for the bus and so forth, and what's the cost on that. So those are input data we would need if we were going to model transit as well, which you can easily, right? We tend to focus more on the highway side of it. It's a little bit better understood, but transit modeling is a thing, right? And so we talked before about that new South Shore connector on the West Lake line. They had to do transit modeling, right? They were trying to predict how many people were going to use that system once it gets built, which is underway now, through there. So once you build your model, and you test it and you run it, right? The next thing is we got to do validation. You got to make sure that it's looking like it's working well, right? And so in our validation, you're checking that you're seeing the traffic and you're seeing the numbers, residential numbers and so forth, and the number of trips that you would expect from a zone, right? If you've got a very low density housing area, but it's got a lot of trips being generated out of it, you might want to check, right? Did we mess something up? Is there something not set right through here? In that. And the way we do that was we do a base condition and we run it. We run a model once we have it built, once we know where the transportation analysis zones are and where the roads are. We run it and we check and make sure that it matches our current counts, right? If it can't even predict what we know our current road counts are, then it's not a very good model, right? So that's one way we validate it. Through there, we have to go back and double check the model construction, right? When I've done these in the past and I've got things blowing up on me, find out that I modeled a 4-lane road as a 2-lane road. Well, no wonder nothing's matching, right? I made a mistake in my design of that model, right, through there. So that's where you start checking all this and making sure that it looks like it's working right, right. And don't just add adjustment factors. This was a problem, or it can still be a problem, right? You can add a weighting function to roads, it's kind of like a friction factor on certain links. And if your model's not working right, it's easy to just throw in a constant, right? That B naught term, maybe in our formulations that adjusts. You can kind of tune it that way, right? You turn the knob and you adjust it so you'll get the count that you have now, right? The volume, your predicted volume on a certain road matches a count you have just because you threw in these adjustment factors, right? There's a bad way to do this, right? If your numbers are way off, that means something is wrong in your formulation. Maybe you don't have enough TASs, or maybe they need to be smaller, right? Maybe the numbers you have in those TASs are wrong, right? You've way overestimated employment in a certain zone, right? Go back and check that stuff, right? Hopefully, if you do a good job of the model formulation and, like, say, your network properties are right, you've got a 4-lane road where there's a 4-lane road inside your model and so forth, and you have the accuracy you want with smaller TASs, right? That will take care of most of that difference you may have from what your model's predicting the number should be and what you actually have there, right? It's not a good way to do it, to just throw in some adjustment factors and say, well, my model says there's 10,000 vehicles a day on this road. There should only be 5, so I'm just going to multiply everything the model says by 0.5. Right? That is not how to do this. You have something wrong in your base formulation, right? Either you don't have enough roads, you don't have small enough TASs, or the data in your TASs or on your network is wrong. So it's a bigger problem, and you want to go back and fix that, because now you're going to use that to predict 20 years in the future, right? Or 10 years in the future, but out to that horizon year through there, you don't want these fixed adjustment factors in there. You want the model to be able to respond to true growth and changes in the network, in your area, in your region that you want through there. All right. So once we get this model built, right, we're going to use it to go through all these steps. And it's a lot of this stuff is kind of iterative, right? To check the model and make sure it's built right, you had to do some of this first. And now we're going to use it to predict things into the future, right? And so trip generation, we've talked about two different ways we can get trip generation numbers. All right, through there, then we go into trip distribution, then mode choice, and then finally assignment, which is putting cars on the road. Right, through that. And we just talked about checking the model. You had to have assignment for that, and then we're coming back around to this. Well, like I say, it's an iterative thing through that. And so we're going to dive more deeply into distribution and mode choice next, right? And then finally end up with assignment is where we end up through this. And right now we're still kind of in generation. How many trips are being generated by type out of a certain zone? And through that. And as we move forward, we should understand some definitions, some glossary terms, right? So an MPO, that's our Metropolitan Planning Organization. These are the people who run the models almost everywhere. Through that, and they are set up by law that any place that is an urbanized zone, which has enough population within a certain boundary, has to have an MPO. So that we can make smart planning choices going forward, and it's not just let's just build stuff and see how it works. All right, we want to be smart about it and model these things. These MPOs, they have to create a transportation improvement plan. It's called a TIP, and so they'll government agencies are members of the MPO. That's usually how it works. And if the city of Valparaiso wanted to add lanes onto Sturdy, they would submit that to the MPO. The MPO would model it, and it would become part of their transportation improvement plan. That'd become their TIP, right? These MPOs then report this to the state in Indiana, it's the INDOT, and they put it into their statewide transportation improvement plan, which is the STIP. And so then they have and it's at a large scale, obviously, right? So it's not going to be fine-tuned. We can't tell exactly what the traffic on Sturdy is going to be, but as a statewide planning model, they do have a statewide model that's going to show that. And of course, at the state level, they're more worried about kind of inner city trips, right? And how much traffic is on interstates and on state highways and so forth. But that's based off of these smaller plans which come out of the MPOs. All right, so the MPO produces TIPs and STIPs, right? And so our MPO in Northwest Indiana is NERPC, Northwest Indiana Regional Plan Commission, through that, and that's our Metropolitan Planning Organization. All right, through that, and they do comprehensive plans into the future. So they've got a 2040. I think they've now got a 2050 plan coming up as well. All right, so they look at all of those things coming out, and they produce that for the Northwest region, which includes Porter County and Valparaiso. Right, and this is some of the products they have. In here, if you were to drill into these, it would show you where all of the major improvement plans are expected to be coming up in the next, this is up until 2040, right? So over the next 20 years, this is where they have expansion projects over a 20-year life span, right, through there. They also model trails and regional corridors, and so they're showing all of these and by priority through that. Right, through there. Yeah, here is transit. So where do they see transit usage through that in different corridors? So again, they are modeling all of those things, right? It's kind of doing a good job. Here's the map of planned improvements over the last 2 years. You can see this was that Vale Park. They wanted to expand that. It still hasn't been built yet. It's getting close, but it hasn't been finished yet. Through there, so that was one thing. US 30 has been having construction on it lately through town. Right over last year, it was closed quite often, and they had lanes closed and whatnot. And here's spot improvements, right? So these are intersection improvement projects that are on the plan in the works, right? And if you click on them, it'll tell you, right? So this one was the Silhavy at LaPorte intersection. Right, which is now finished, right? But that was in their plan in that 2018 to 2021 time frame, which it did. It is now improved, right? So they modeled that. They modeled that improvement right through there. And those MPOs are charged with maintaining these models, and any project that you plan as a government agency, if you're the city or the county, you have to get it formally accepted into the tip, right? Especially if you want any federal money for it. They're in charge of keeping track of all these things and putting them in there through that. So as the city is a member of the MPO, they would submit that project, the Silhavian and LaPorte roundabout, for example. They submit that to the MPO. The MPO then puts it into their TIP, it's the Transportation Improvement Plan, right, for that. And then they're going to model that in their future. For capacity, but also emissions is a big deal in Northwest Indiana, right? So a lot of pollution comes from cars, and so modeling how the change in the road network is going to affect delay and how much cars have to idle, right? That's going to affect the emissions for that. That's it for today. We will have more coming up on transportation modeling next time.